Alright, so in the previous video, we have looked at the pre-order traversal. So now, continue the pre-order traversal. Let's look at this problem, 145 binary tree post-order traversal. So here the problem is that given the root of a binary tree, so we are required to return the post-order traversal of its nodes values. So in the post-order traversal, we first traverse the left subtree, and then we traverse the right subtree, and finally we traverse the node. So let's look at one example here. So in example 1, so when we traverse this one, so we first look at the root and we check its left subtree. So its left subtree is null, so we go to the right subtree, that is the tree with root 2. And then for this subtree, we're going to do the same. So we look at its right subtree, that is 3. So we are going to have a 3. And then we check its right subtree, that is null. So we come back to look at the root 2 itself. So we get 2. So once we get 3 and 2, we finished traverse the right subtree of 1. Then we look at the root 1. So we get 3, 2, 1. So this is the example of post-order traversal. So again, second example is the trivial example, and the third one is a very special case because we have a single node tree. So we just return the root value. So again, here is a follow-up which says that the recursive solution is trivial. Could we do it iteratively? So as mentioned in the previous video, we are going to try to write this traversals in iterative way, because the iterative way reveals more detail, and also we want to use these traversals as foundations to solve more complex problem. So, but for the purpose of completeness, so I will first write a recursion solution just for the digest of the definition of post-order traversal. So let's look at this recursive solution. So first I will check if the root is empty or not. So if not root, we're going to return empty list. So otherwise, we use the definition of post-order traversal. I'll first traverse the left subtree. So I will self-call post-order traversal. So we traverse the root left, and then I'm going to traverse the right subtree. So root right, and finally I add the root value itself. So so here the plus means list concatenation, because what we want to return is actually a list. So now with that said, let's first test this solution. So it passes the test cases. So in this sense, so this recursion solution is sort of trivial. So now let's look at the iterative solution. So I will use the same line of idea as I wrote for the pre-order traversal. So notice that when we do the pre-order traversal, we emphasize one thing. That is, we need to first do the right child and then do the left child in the pre-order traversal. So now here we want to do the similar thing, but as I mentioned, so this pre-order traversal and post-order traversal has connection with depth first search in the graph, in general graph. But in the binary tree, there's a concept called left and right. So I want to change the thought a little bit. Here, I want to reverse the right and left. I want to interpret right as left, and similarly left as right. So what I want to do is the following. So first, I would like to check the special case if not root. So I'm going to return the empty list. Then I'll do the standard traversal. So for that purpose, I'll first initialize a result a variable which initially is an empty list, whose final state is what we want to return. And then I want to initialize a stack. So the stack initially holds one node, that is the root node. Then I'm going to traverse the tree. So in other words, it's a while loop. Then I'll first pop this node currently in the stack. Then what I want to do is I first add the value here. So node value. So this is one part. So next is the crucial part. So in the pre-order traversal, we emphasize that we first add the right subtree and then do the left subtree. So here a natural thought is we have pre and we have post. We add the left child first. So let's first do that. If node left, so I'm going to do stack append node left, and then if node right, I'm going to append node right. So here we changed the order of putting the left and right child into the queue. So here what I do actually is first left and then right. So in effect, basically it's corresponding to interchange left or right. So make an opposite interpretation of the direction, right? Then we want to return. So here again, this return actually is not trivial. So in pre-order traversal, after we add first right child and then left child, then we are going to return the result itself. But here, because we interpret left as right and right as left by adding node left first and node right first. So when we do the return in this format of code, we shall return result reverse. The reverse actually corresponding to interpret the result left as right and right as left. So that's a crucial point. So with that said, let's test the code. So here S is not defined. So here S is stack. So I'll use this as S. So I'll test the code. Yeah, it passes the test cases. So actually, this is one way of writing the post-order traversal algorithm. So this way actually is the same as the pre-order traversal if we interpret left as right and right as left. So here, this corresponding if we reverse back, we are going to get pre-order traversal. So in short, the post-order traversal and the pre-order traversal is symmetric. So that's basically the solution for this problem, and also it's what we want to convey. So we would recommend, if you have time, to have a look at the explanation about the pre-order traversal video. So with that said, so we're going to have another video on the next video or on in-order traversal. Thank you very much.